Hey guys, I wanted to do a quick video on limiting reactants and percent yield and be able to review that concept with you. So let's go over to the next slide. I'll get there eventually. All right, so in this problem, we want to determine the theoretical and the percent yield of aluminum oxide. So theoretical and percent yield of aluminum oxide. Here's the information that's given to me. 50 grams of aluminum reacts with 25 grams of oxygen. So 25 grams of oxygen, 50 grams of aluminum. And then it also gives me 42 grams of aluminum oxide is obtained. I want to circle that word because that's a keyword for something there. So let's talk about a couple of things. First of all, what is theoretical yield? The theoretical yield is the calculated gram value of my desired product. So in this case, since we want aluminum oxide, it will be whatever grams of the aluminum oxide that I calculate based upon the information given to me. The second thing is, what is percent yield? Percent yield is found from the actual yield, so I'm just going to put an A, divided by the theoretical yield times 100. Now, actual yield is what is given to me in the problem or what I figure out in my experiment. So if I'm actually working this experimentally, then whatever I find experimentally, the grams of the aluminum oxide will be my actual yield. My theoretical yield is what I calculate, and we talked about that just a second ago. If I multiply by 100, that will give me my percent yield. So we know that we're going to have to calculate this theoretical value. And I know that this actual yield must be given to me somewhere. So where do I find it? It's all based upon this keyword, obtained. So wherever you see the word obtained, whatever is basically connected to that. So the amount of the product that's connected to that word, that is going to be my actual yield. So this 42.8 grams is going to be plugged in there for the actual yield. We now have to use the information that's given to us to figure out the theoretical yield. So when you're working with any type of stoichiometry, you have to have a balanced reaction first. And so we have the reaction here, but we don't have that reaction balanced. So in order to balance that, we're going to have to play around with these a little bit. If I put a 2 there, a 3 there, and a 4 here, I should have a completely balanced reaction. Now that I have a completely balanced reaction, I need to ask myself, how am I going to figure out this theoretical yield? What information is given to me? So if I look up here, I'm given 50 grams of aluminum and 25 grams of the oxygen. So I'm basically being given information about this reactant here, as well as this reactant here. Whenever that's the case, what that means is that one of these reactants is going to be the limiting reactant. That means that it's going to run out. It's going to prohibit how much of the product that I can actually make. It's going to dictate how much of that I can make. So I have to work a rice chart anytime I am given information about both of my reactants, because I have to figure out who's my limiting reactant. Now, when I am working with rice charts, I cannot stress this enough. You have to work with moles. The reason why is because stoichiometry is all about mole-to-mole ratios. I can't do gram-to-gram relationships because everything has different masses, but the common factor between everything is moles. So if I can get everything to moles and work with that in my rice chart, I can figure out who my limiting reactant is, and then I can also figure out what my theoretical yield is of this product. So I want to draw your attention now to my little whiteboard. We were given 50 grams of aluminum, and then we were also given 25 grams of the oxygen. So the very first thing that we have to do is we have to convert these grams to moles. We do that by dividing by the molar mass of each. This is the molar mass of aluminum. This is the molar mass of oxygen, which is O2. From there, I find I have 1.85 moles of aluminum and 0.78 moles of O2. Okay, so now that I have my initial values, 1.85 moles for aluminum, 0.781 moles for oxygen, and then 0 moles for my product because I haven't made that yet, I have to figure out which one of these is limiting. Now, I cannot directly look at 0.781 and 1.85 because this is not a one-to-one relationship. So in order to compare a one-to-one relationship, what I do, now this is just scratch work on the side. I have it right here on my whiteboard. What I have to do is take the 1.85, which is the initial moles, and divide by the coefficient 4. What that is going to give me is the information for 1 mole of aluminum. So 0.463 for 1 aluminum in that reaction. Then I'm going to do the same thing for the oxygen. So take 0.781, divide by 3, because that's the coefficient that I see for oxygen, and that's going to tell me that I have 0.260 moles for 1 oxygen in the reaction. I can now compare these two values because I'm comparing 1 O2 to 1 aluminum for what I have in the reaction here. If I look at those two numbers, this number is smaller. So what that tells me is that oxygen is my limiting reactant. Since I know that oxygen is my limiting reactant, what I'm going to do is use all of it. So looky here, I have minus 0.781 in my C line. Now, here's the difference. I line means initial, what I have at the beginning of the reaction. The second line here is the C line. What that stands for is change. So that's what is reacting. So how much aluminum is reacting, how much oxygen is reacting, and how much of the aluminum oxide is being produced. Then you have your very last line. Your last line is what is left over, what you have at the very end of the reaction. So now that I know that oxygen is my limiting reactant and I'm going to use all of it, the question is, how do I find these two numbers? So how I find this number and this number here is by basically doing dimensional analysis in my head. All right, so think about it. If I were to give you 0.781 moles and I told you to transfer that to moles of aluminum, what you would do is you would set up a dimensional analysis. You would say 0.781 moles. You would do a mole to mole ratio, which is 3 to 4. So you would divide by 3, so you have moles of oxygen going away, and then you would multiply by 4 moles to get into aluminum. All right, so when you're finding these other values for your C line, you're basically setting up dimensional analysis in your head. How you do that is you take your limiting reactant value, so that's this 0.781 here, and you are dividing by the coefficient of your limiting reactant, so 0.781 divided by 3, and then you're taking that number and multiplying by the coefficient you're trying to get into. So 0.781 divided by 3 times 4 gives you this quantity here, 1.04. So that is how much aluminum is reacting. Then, to figure out my quantity of aluminum oxide that's being produced during this reaction, how I find that value is, again, take your limiting reactant, because you remember, your limiting reactant dictates how much is going to be used up and how much is going to be produced. So I take that limiting reactant value, divide by the coefficient of the limiting reactant, so 0.781 divided by 3, and then I multiply by the coefficient that I'm trying to get into. So 0.781 divided by 3 times 2 gives me 0.52. Now, to figure out my ending values, all I do is work the math. Since this is reacting, it's decreasing by 1.04. Since this is being produced, it's adding 0.52 moles. So I have 0.81 moles left in excess, 0 left of my O2 because it's my limiting reactant, and then 0.52 moles has been produced for the aluminum oxide. Okay. So now that I know how many moles of my product is produced, I now can go back and figure out my theoretical yield. Remember, theoretical yield is your gram amount. So I'm going to have to take this 0.52 moles and convert that to grams. Once I know the grams, then that's going to be my T here, my theoretical yield, and I can find my percent yield from there. So over here on my whiteboard, here is my work. I took the 0.52 moles, converted that to grams. The molar mass is 102, and I found that there's 53.04 grams that theoretically should be produced of the aluminum oxide. So remember, my calculated value is my theoretical yield. Now to figure out my percent yield, I'm going to take my actual value, which is what's obtained, what's given to me. So that's the 42.8 grams that was in my problem right here at the aluminum oxide. And then I divide by my theoretical yield, 53.04, multiply by 100, and I get 80.7% yield. So I hope that video was a little bit helpful. Limiting reactants, being able to do this stoichiometry stuff is super important, and we're going to be using this throughout our whole course. So I hope you get a good grasp of it, and I hope this video helps. See you later.